Okay, so today we're going to cover chapter 42, the Kruskal-Wallis test. And this is the non-parametric test that's the equivalent of ANOVA. So last time in chapter 41, what we did was we looked at the Wilcoxon-Mann-Whitney test, and that was to compare two groups. It was the non-parametric equivalent to the two sample t-test. Now we're going to look at comparing the means of three or more groups. And as with all non-parametric tests, they have the advantage of not needing the assumption of underlying normal populations. All right, so basically it starts off the same way as what we did last time. We are going to combine now the three groups instead of two, into one ordered list from smallest to largest. And then we're going to assign them a rank from one. In this case, we're going to have, here's our three groups. We're going to continue this example of comparing different versions of the final and the null hypothesis. Before we had two groups, and the null hypothesis was there's no difference in the level of difficulty between the two groups. Now suppose we had three versions of the final, which is basically the way I always did it for Stat 100 and may do it for your final. So now we have three versions of the final, and suppose I'm giving these versions to a small group of students before the final, and I want to make sure that the final is really at the same level of difficulty for all. They're equivalent. I would hate to give versions that were unequal difficulty. It wouldn't be fair. So suppose I randomly, here's a group of what? 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3. Okay, so here's a group of 16 students, and suppose I randomly gave them the three different versions of the final, and this, I put, okay, there's 5 in group A, 5 in group B, and 6 in group C. And these were their scores. Wow, this person did terrible, 10, and this person got 100. Okay, so remember what we're going to do here. We are going to replace all these values with rankings. That's step 1. So here, we're going to order these 16 numbers, and that's what I did here. You take the data, and you order them from the smallest, 10 is the smallest, all the way up to 100 is the largest, and you rank them. Now, they're going to be numbers 1 through 16. Now, if you have a tie, like these two 70s, here's a 70 and here's a 70, what we do is instead of assigning a 5 and a 6, it would normally go 4, 5, 6, 7. Instead of that, we're just going to give both of these the average rank of between 5 and 6. That's 5.5 and 5.5. All right, so now we've got step 1 and 2 down, and now what we're going to do is we are going to translate these actual exam scores into just ranks. So let's do that. So what's 10? 10 is a rank of 1, right? 60 is a rank of 4, etc. 70 is a rank of what? 5.5. And then 80 is 8. And 100 is 16. All right, so we have those 5 numbers, and then we're just going to sum them, take the rank sum. So the sum of all these, the sum is equal to 34.5. All right, so that's what we're going. So that's our observed rank sum. Let's write that down. So these are our observed rank sums. And we're going to do that for all the groups. Okay, so for this one, we're just going to take, okay, so 50 is 3, so 70 again is 5.5, 81 is 9, 85 is 10, and 13. Then we take this sum, and we add them all up, and I got 40.5. All right, and the last one. So 20. So we have 2, and then 75 is 7, 11, 12, and 14, and 15. And then we sum all these up. Okay. So those are our observed rank sums. And now you might as well check that, you should check that these have to sum to the numbers between 1 and 16. So remember, when we add up the numbers between 1 and n, we use this formula. 1 plus 16, 2 is 17, 2 plus 15 is 7, 3 plus 14 is 17, etc. Right? 17. And so we get this formula. So in this case, it's 16 numbers. And I see sorry, this should be a 16 here. Okay? All right, so 16 times 17 over 2. And we get 136. Okay, now let's make sure that those sum to 136, and they do. So let's check that 34.5 plus 40.5 plus 61 does equal 136, and it does. Good. Okay, so now we're going to compute a statistic. Now, last time we computed the z statistic because we said that the, we're changing these numbers to just integers between just 1 and 16. There's a, so this is so these sums will very quickly, if there's just two groups, the rank sum will follow the normal distribution, but now there's 3. And our test statistic can't be a z anymore because we can't boil down the difference between the 3 groups into a single signed number. So we can't do a 2-sample z test or t-test. We have to look at the overall pattern of differences and do a chi-square test, the way we always do when we compare more than 2 groups. Okay, so we have to do a chi-square statistic. And so this is going to be our statistic. It looks very much like the chi-square statistic we're used to, and the observed minus the expected squared. But first, so we have to get the expected sum for each group. All right, so let's do that. The expected sum for each group would be what? For the first group, for each group, you would expect the sample size here of the group times this part, which is the overall average, the 17 over 2. See, in other words, for each one of these groups, you would, of course, they're going to be above and below average, but if you think that there's absolutely no difference between the 3 groups, which is what the null is, then of course you would expect each group to just be, its sample size times the average. All right, so here, this group has 5, and the average is 17 over 2, so you'd expect this one to be 4. This is the expected rank sums, and you'd expect this group has the exact same thing. They just both have 5 numbers, so it would be exactly the same, 42.5 right there. In this instance, this has 6 numbers. It's going to have a bigger rank sum, 6 times 8.5, which is 51. Okay, so these 3 numbers are now the expected ranks. And now, by the way, this will be given to you on the final, right? So you do not have to memorize this formula. But you should know that the degrees of freedom, well, for all chi-square tests, are going to be the number of groups minus 1. And in this case, it's going to be 3 groups minus 1, the same thing. But this part will be given to you, so let's just make sure you know how to compute it. So you'd say it's called an H-stat, and it's 12 over 16 times 17, because we have 16 numbers total, times the sum of what? Well, for each group, we might as well just, I don't have to write the sum, let's just sum it. So for each group, what are we going to have? The observed, which is 34.5 minus its expected 42.5 squared over the sample size. So that would be over 5. And we'll do the same for the next group, and that's 40.5 is the observed minus its expected, which is again 42.5 squared over its sample size. And the last one is going to be over 6 because we have 6 in the sample size, and the observed here, it's 61, and the expected is 51 squared. So that's it. All right, so we have 12 divided by 16 times 17 here. And let's simplify this. So what is this right here? 34.5 minus 42.5. So we get negative 8 squared over 5 plus, here we have negative 2 squared over 5. And here we have 10 squared over 6. Now note that these three inside the parentheses here, before, if you didn't square the differences, you're always going to sum to 0. So you have to square the differences here, otherwise our statistic would always be 0. Okay? And so that's a good way to check. Make sure the negative 8 plus negative 2 plus 10 inside here equals 0, otherwise you've made a careless error. Okay, so we do this, and I got 1.344. So we are going to compare this stat. We're going to compare this to a chi-square critical value with degrees of the curve with degrees of freedom equal 2. So we want to compare this to a chi-square critical value with degrees of freedom equal to 2. 3 groups minus 1. All right? At what? Alpha equals, why don't we do 5%? And which is what? We'll find that. Which is, what is that? So we can look in the chi-square table, and we'll do that and find that, okay, so degrees of freedom 2, and here's 5%, so we are going to compare to 5.991. So if it's, we need at least a 5.991 to reject the null, and we don't have it. So just to refresh your memory, let's just look at what that would look like. So basically the chi-square curve would look something like, be very lopsided here. And our critical value at 5% right here is 5.99. That is 5 point. We need, we need that extreme a difference from what we'd expect or more to reject the null. Because the null is that all the groups, that's the likelihood that we would see this big a difference or more extreme just by the luck of the draw. And we got 1.3, we're way here. We're just way up here. This is our actual chi-square stat, so our p-value is huge. So we're not going to reject the null, okay? So we can say that. We'll say 1.344 is greater than 5.99, so don't reject the null. Which is great for me because I wanted those exams to be the same. All right? We don't reject the null. It has a very large p-value. And if you want to find out the exact p-value, you could look on the computer and get that. Okay? So that's the Kruskal-Wallis test. And you have homework on this. And I think that's all for this video. Bye.